taking that alcohol and reacting it with PBr3. What are we going to get from that?
Would PBr just replace one of the PBRs? Replace the not the PBr, the BR replaces the OH.
Who was that?
Juanita Smith.
Yeah. You're right. You're gonna get an alkyl halide that looks like this, right? Is that right?
Yeah.
Mm-hmm. And then what happens when I take that alkyl halide and react it with magnesium? What happens when I react it with magnesium at low temperature in ether? This is all stuff we've done already.
It's gonna be magnesium.
You make it bromide. Go ahead. Are you saying that you're gonna make a granular?
Yes.
Okay. I just want. So the granular is gonna be here. That's MgBr. Is that right?
Yep.
And then what happens when we take the granular and add it to benzaldehyde, which looks like this? What happens? And then so that'll be, and then followed by you. Of course, you're going to add some H+. What kind of reaction is that? What happens when you add a granular plus an aldehyde? What do you get? Granular plus an aldehyde or a ketone gives you a what?
Alcohol.
Alcohol, right? So we're going to get this alcohol, because obviously at the end of that reaction, you're going to have to get this carbon right here. Is that right? Well, this is the carbon that's reacting now from the granular. Make sure I didn't add a carbon. I did. Don't want to erase all that. Erase this side though. I gotta move this up. Are y'all following that? So this is the new carbon-carbon bond that we made right here from that reaction. Now I can move it back. Smaller. All right. Anybody got a problem with that? With the granular adding to benzaldehyde? All of these are reactions that we've already done. There's nothing new on this page except for that last reaction, which is a Swern oxidation. Right, and so the Swern is a way to sorry about that. The pen wants to act stupid, but it's okay. I get some water on here, son. All right. All the technology wants to act stupid today. Come on, man. All right, let me do that. Let me try sharing this again. So the Swern is a way to oxidize alcohols to carbonyls. All right, that's what it does. It's a And you can you can look up the reagents. I'm not really concerned about that part or the mechanism. I just want you to know what it does. So if I have an alcohol, like a secondary alcohol like this, and I treat it under swirling conditions, right, I'm going to get a ketone. So it's a way to oxidize alcohols up to carbonyls. Right, it's primary or secondary alcohols. Right, so if I take that last, didn't realize I had all this room down here. Let me move this stuff, some of this stuff. If I take that last reaction, and I treat the alcohol with swirn, what should happen?
Would the alcohol just go back to a carboxyl, like how you just said?
Yeah, you're just gonna get the alcohol just gonna get converted into a ketone.
Yeah.
Right. So right here, if I take that and treat it with swirn, right, I'm just gonna get this, right? That alcohol is gonna become a ketone, right? So we basically have 3 reactions or 3 products that have different NMR. So we're gonna look for this NMR, this one, and this one. Actually move this over. All right, so let's look at the products and see how many signals each one of them should give us. What do you think for the first one? The alkyl halide, how many signals should I get for that?
Is it 4?
4? Let's see if we can pick them out. All right, so you know you got a CH3 here. So 1 signal for that, here, here, here. Should get 4 signals. And then this should be a triplet. This should be a pentet. And this should also be a, no, sorry, sextet. This should be a pentet. And then this should be a triplet. Where should that triplet be on the carbon that's closest to bromine? Remember, for your proton NMR, 0 to 10. So where should it be on that scale?
Should it be a little downfield?
Yeah, downfield, somewhere between 3, 4.5, somewhere like that. So the granular, we don't have a NMR for that, I don't think. What about over here? How many signals should you see for the alcohol? Of course, this is a CH3. Is this chain going to change at all as far as how many signals it gives?
I'm not sure. What do you
It
mean
shouldn't.
change?
The chain should still give you 4 signals.
Oh,
All those protons are still non-equivalent, right? And then this proton right here is going to show up, and then of course you're going to have your aromatics. You'll have your aromatic protons. All right. So over here, what do you think? What proton do you lose going from the alcohol to the ketone?
the proton next to the alcohol.
What was the name of that? Anybody remember what we call that proton that's right there adjacent to the OH group? It's called a carbonyl proton. Probably forgot. I think that was Friday. But that proton is no longer there. When that alcohol gets oxidized up, you're going to lose that. So that's one of the key things you look for in the NMR, going from when you take the NMR of the ketone after you do the swirl, you look for the disappearance of that proton, right? And it should be a pretty prominent triplet that's easy to pick out. All right, so let's look at the spectra and see if we can figure out what's what. We should have 3 spectra. All right, what do you think? You have aromatic protons, right? You got some alkyl protons down here. Right, you got some alkyl protons. What do you not have? All right, let's look at the infrared. Infrared says you have stretches at 3,000, 2980, and 1760. What do you think that 1760 is corresponding to? That's gonna blow the whole thing open. If you can tell me what the infrared stretch at 1760 represents, it's gonna blow the whole problem open.
Is it the ring?
Say again.
Is it the ring?
No, remember the aromatic stretching is about 3,000, and it's really weak. But 1760 is a functional group that's really prominent, and it's a really strong stretch. But it's not the ring. The ring is probably going to be that stretch at 3,000. All right. What do you think? Think about it. 1760 it's a functional group that
Is it the carbonyl stretch?
carbonyl stretch. 1760 is your carbonyl stretch. Good. Who said that?
I did, Leah.
Okay. Kimbrough, right?
Yes, sir.
Okay. Nice work. Nice work. It's the carbonyl stretch. Good. That blows the whole problem open, right? Because there's only one of these products that has a carbonyl in it. Which one is it?
The last one.
The final product. So let's draw that on here. And see if we can pick out the signals. We know we're just going to label this as aromatic, right? How many protons, if we integrated all 3 of those signals up in the aromatic region, which is always going to be the same, somewhere between 7 and 8.5, that's where your aromatics show up. How many protons would that integrate for if we integrated all 3 signals? We're just gonna keep doing stuff until y'all count them.
Oh my goodness. Are we counting the proteins on the ring or as a whole?
Yeah, the ring. The question. The
I didn't
question
hear the
was,
question.
how many? What would? How many protons would those signals integrate for in the aromatic region if I integrated all three signals? How many protons would those signals represent?
So I'm assuming 4.
4. That's right. You got 4 aromatic protons, and you got 3 signals. And if I integrated the whole section, it would integrate for a total of 4 hydrogens. Remember the example we did with the pyridine ring, the nitrogen containing aromatic ring, and the whole section was integrated, and the total was 4?
Mm-hmm.
All right, never mind.
Okay, but one question.
Go ahead.
So for these lines, how sometimes you see how they're kind of doubled up? How would I know if they're together or sometimes they're separate? Because sometimes they could just be really close to together. Sometimes you'd be like those two are a pair.
You mean like right here?
Yeah.
Yeah. So so with the aromatics, the trick to identifying aromatic protons is to remember where they show up. Right? They're always downfield, and they're always somewhere between 7.5 or about 7 and 8.5. Always. So that's a giveaway as far as the signals. Now, as far as the number of signals, right? That means if you look at the number of signals and the number of protons, what it's saying is that you basically have 3 protons on that ring, or 3 signals for 4 protons. So two of those protons are going to be equivalent, right? So if I'm looking at the ring and I'm thinking about my test for equivalence, what do I do? How do I test for equivalence? Anybody remember?
You change one of the to like a chlorine or something to see if it'll change.
Yeah, it'll change. So right here, if I put another atom here or here, I'm going to get the same thing, right? It might not look like it, but with this carbon-carbon single bond here, you can rotate around that bond. So those 2 protons are going to show up for the same signal, right? And then that's a proton right here too. Ain't nobody say a word. That's all right. We can make it. So those 2 are going to be the same. And then same here. These 2 will be the same. We swapped them out with a different atom right here. I'm going to put a Y here. So that's a signal, right? So that's 1 signal for those 2, 1 for the other 2, the X's. And then you're going to get, I'm going to call this one Z. You'll get a signal for that one. That's why you only see 3 signals down there, because you have some equivalence on the ring, right? So the 2 protons that I have labeled as Y are equivalent, and it might not look like it, but you can, if you rotate around that carbon-carbon bond, this proton right here is going to end up where this one is, right? If you rotate around that bond. And the same thing with the ones labeled as X's, right? These 2, if you rotate it around, you're going to see the same thing. Stop spying on me. Sorry. My phone just all of a sudden just starts recording me. All right. So that's why you see 3 signals for 5. It should be 5 protons, not 4. I apologize for that. But nobody caught me. That's not good. So close to the exam. Somebody should have been like, Dr. Russell, you messed up. All right. So that's the aromatic part. Did that answer your question, by the way?
Yeah, sort of.
Sort of.
Mm.
You don't sound real confident about that. Like, yeah, whatever.
No, it's just sometimes like
So what's the confusing part? Is it the splitting patterns or is it the number of signals that's confusing you?
I think it just be the splitting patterns and the splitting patterns. Because then sometimes it'll be like splitting patterns, but they'll be for two different types of groups, but they're so close together. But then sometimes you'll be like, actually, this is, I don't know.
Yeah, so let's look at the Y protons. What should the Y protons be? How many neighbors does the protons at Y, that I have labeled as Y, how many neighbors do they have?
Two.
Two neighbors? You sure? You got a neighbor on this side. Is that right?
Mm-hmm.
And what about on this carbon over here? Do you have any hydrogens on that carbon?
No.
No. So it's only one neighbor. So how many?
Oh, I was also counting the other one at the bottom. I thought we did.
Can't count that. It's too far away. You can only count what's immediately next door.
No, I mean I was using that hydrogen and counting the hydrogen next to it as well.
Oh yeah, but remember those two are equivalent. The one that's labeled Y and Y, they're equivalent. So you only have to worry about one of them. But then when you integrate the signal, that's when it's going to show up that it's actually two protons. Because remember, the integration it tells you the number of hydrogens.
Mm-hmm.
Right? So that should be what? What should Y be? Multiplicity, splitting pattern wise. What should it be?
It should be a doublet.
Doublet. Good. Do you see a doublet down in the aromatic region?
Yeah.
Right here, right? What about X? What should X be?
It has two neighbors.
Mm-hmm.
So a triplet.
Do you see a triplet down there? It's not symmetrical, but do you see a triplet?
Mm-hmm.
Right here, don't you? And then the Z proton is gonna be a triplet too, but it's kind of messy looking, but it's kind of down up in here. But it's messy because Z, again, if the X protons next door to it, if it's splitting with both of them, then you might have a little bit of complex splitting for that one. So that's why it looks so messy. But the other ones you can pick out with no problem. All right, let's see if we can keep working on this one. What do you want? Where do you want to start on the chain? You pick. Oh, let me erase this. I'm gonna change that. You want to start at the CH3 at the end?
It doesn't matter.
Let's start here. What should that be?
It should be 1, 2, 3, 4.
It's got two neighbors right here, right?
Oh, we talk about neighbors. Okay.
It should be a triplet. Is that right?
Mm-hmm.
Where? Because you got another triplet
right there
at 3. Is it going to be upfield or downfield?
Upfield.
Upfield. Good. So we're going to label that as, since we're going backwards, we're going in with alphabet. And this is a DUI test. So we're going to label that W. You know, that's one of the things they make you do. Say the alphabet backwards. Even if I'm sober, I would be tripping over stuff. So that's going to be upfield. It's going to be a triplet. And we're going to call that W right there. All right. We okay with that?
Mm-hmm.
Yes or no?
Mm-hmm.
Yes.
All right. And what about the protons next door to that? Right here. What's your day
It'll
be?
be 5.
Good. So you're gonna get a what for that? What splitting
A
test?
6 set.
Good, good, good. So you get sextet for that. Let's see if we can find that down here. It's gonna be one of these two, right?
Mm.
So let's count those up. Let's see which one is 6. This is 1, 2, 3, 4, 5, and this is 1, 2, 3, 4, 5, 6. So it's gonna be that one. So we're gonna call that V. All right. Questions about that? Okay. So what about the one here? The set of protons here.
It'll be 4.
4 neighbors. So
I have a pentet.
pentet. Good. Excellent. That should be a pentet. And you can see that we already counted that, right? It's right down here.
Okay, yeah, that was my question related to that. Like, you see how these two signals are super close?
Mm-hmm.
You just have to figure out the whole.
So what you're looking for, like, remember, is it's following all these type of signals are going to follow that Pascal's triangle, right? So they're going to always have this symmetry to them, where the outer bands are a certain height, like if it's a quartet, and then the inner bands are going to be a certain height. So you're kind of looking for that symmetry, right? They don't just kind of blend together. Like we counted out for that sextet. You can see you got the 2 outer bands here.
Mm-hmm.
Let me make that smaller, sorry. All right, you can see you got the 2 outer bands on the sextet right here and right here, right? And then you got these 2 bands here. And then these 2 bands here. So if it's a signal that's not really a complex splitting signal, like a doublet or doublets or something like that, it's always gonna have that symmetry because it's gonna follow that Pascal's triangle. So you're gonna have the shorter bands on the outside, and the intensity is going to increase as you move towards the middle of that signal.
Okay.
Does that help?
Yeah.
Yeah. And if you look at the pentet, it's the same thing, right? You got the outer bands right here. But even though they're not the same height, that's part of the pentet. All right, so then you have your 2 inner bands, and then you have your middle band. But it's all the same signal. It's just split up into those lines because of that Pascal's triangle.
Okay, so if it was like doublet or doublets and stuff like that, that would tell you that there's complex splitting.
Mm-hmm. And all your peaks would be the same height. So a doublet or doublets would look like a quartet, but all your peaks will look the same height. See how the difference in a quartet, 2 outer lines are shorter than the 2 inner lines?
Mm-hmm.
But for a doublet or doublets, right, all your lines are going to be the same height.
Okay, yeah. That's why I was confused.
Yeah, that's a good question. That means you're really thinking about this. I like that. All right. Let's see. We got one more triplet left. And we got one more set of protons left, right? Which is be right here.
Mm-hmm.
Right? And they are downfield. What is that? This will be U. Right? Hold up, that's not U. The other one is U. This is U, right? And those will be T. Is that right?
I'm not good with backwards alphabet either, so I'm not.
That's okay. This was U right here. And then that would be T because we're working backwards. I know that's so dumb of me to do that. It's already confusing. And then I'm up here trying to do the alphabet backwards. Like a dummy. Just know if you ever get pulled over and they make you do it backwards, you can take as long as you want to. You don't have to go at a certain speed. So just take your time. All right. So that's gonna be T, and that's gonna be a triplet. And why is it at 3? Why is it at 3? Somebody help me with that part.
It's right next to that carboxyl.
It's right next to the carbonyl. Very good. So anytime it's your carbon where your protons are is bonded to a carbon that has a sp2 atom or some electronegative atom, it's gonna get shifted downfield. What's that called when protons get shifted downfield? What's the term that we use for that?
Deshielding.
Deshielding. Excellent. Right? So it's going to be deshielded because of that sp2 carbon, and it's going to be a triplet because it's got 2 neighbors. And remember, from the NMR, what we take away from this is 4 things we take away. Number 1 is what? Non-equivalence. Right? That's going to be reflected in the number of signals. What else do we take away? There's 4 things that from every NMR you can get. Connectivity.
Location.
Good. Location.
Multiplicity.
Yeah, so that's going to be my...
The number of hydrogens.
Yes. So multiplicity that's going to be based on the connectivity. If it's connected to a carbon that has 2 hydrogens on it or 3 hydrogens, so on and so forth, you're going to get different splitting patterns. Location is the chemical environment. Is that right? Upfield or downfield? And then, did you say the number of hydrogens?
Yes, integration, right?
Mm-hmm. So the number of hydrogens, that comes from the integration. Right, those are the 4 pieces of information, main pieces of information that you can take from an NMR. There's some other information, but these are the 4 main pieces of information that we take from any spectrum. The number of signals, the number of hydrogens each signal represents, the location of those protons, whether they be in electron-rich or poor environments, and the connectivity of the carbons where those protons are. All right, let's go to, got time to do one more example, I think. What do you think here? Spectrum B. We're going to stop on this. And if I'm going to send this, upload it to Blackboard, if you finish B and C, I'll let you turn it in for a bonus assignment. We did the hardest one already. And I'll create a link so when you turn your homework in for the exam, you can turn this in as a bonus assignment. And the points are up top. That's a big bonus. Look at that. Ooh, that ought to make you salivate. 15 free points. Never mind. It's Monday. Y'all ain't catching nothing. It's Monday, and it's the last part of the semester. I was just like, bro, hurry up. Get to the point. All right. What do you think? Spectrum B. This is free points. If you can tell me which compound this is, I'm going to put it on there. You got to pick out the signals, though. Look at and we don't have any infrared data here, but what do you think?
Can we look back at the reaction?
Yeah. No problem. And it's not the star material. We don't have anything for the granular or the star material. But these are the reactions up here, up top. This was the first reaction that happened, where you converted the alcohol into an alkyl halide.
Would the second one be for the?
Come on.
The first part.
The first product.
Mm-hmm. I
wish I could give you a virtual high five. Yes. It's going to be for this, right? That's exactly right. How do we know it's for that? What's not present?
That BR.
Mm-mm.
I was thinking because the BR was there and I saw something down.
Look at the spectrum though. What protons are not there? Look where it stops. It stops at 4, right?
The ring?
The aromatic. There's no aromatic protons.
Mm-hmm.
So it can't be either one of the products that have the aromatic ring involved. Are you following? That's kind of like working backwards. If you look at the spectrum and you don't see the aromatic protons, then it's got to be something that does not have the aromatic protons incorporated. Is that right?
Mm.
Yeah. So I'm gonna leave it up to you to pick out the spectrum. I mean, pick out the protons, which one's a triplet, which one's a doublet, so on and so forth. Let's go down to C. What do you think about C? Look at the infrared and it's gonna blow the doors off if you look at the infrared.
So you know the ring is in there.
The ring is in there. What else is in there? Look at the infrared. Tell me what you see. 2 stretches in the infrared that give it away.
Isn't there alcohol? Is there alcohol in there?
Which one? Which stretch is the alcohol stretch? You're right. Come on now. Come on.
Like I'm under pressure.
You're under
It's,
pressure.
33.
3,300?
Mm-hmm.
I want.
That's your OH stretch.
Okay.
The 3,000, that's your aromatic stuff, right?
Mm-hmm.
And then somewhere about 2,900 or so, that's where you see your alkyl stretching, but I just didn't list it. Because the alcohol is what's going to give it away. And then 1050, that's your CO single bond stretch. All right. So it is, that's your alcohol. So it's going to be here. Right. So you need to pick the peaks out for that one. I don't know what happened on Friday. Something was going on, I guess, with my Wi-Fi or something, but I couldn't get the notes. I emailed them to myself, but they never came through. So I'm gonna try to email Friday's notes again, and I'm gonna send this. I'm gonna put this on Blackboard. You finish it. If you finish it, and match all the peaks up with the spectrum for here and for spectrum B, you can turn that in, and it'll be a bonus assignment. It'll also help you prepare for the exam too. All right, any questions about anything? This was a good discussion. Thank y'all for those of you who actually chimed in, thank you. Even though you felt pressure. Pressure is good sometimes. It'll bring out the best in you. Oh, this is the OH proton. Do you know that's?
Is OH showing up on the chart?
Right there.
Yeah.
So I was gonna be in the same little area, 3.5 to 4. It's gonna be not well resolved. But what do we know about OH and NH proton? Do they split? Do they cause splitting?
No, right?
No, they don't split. So they do not couple with other protons.
Mm.
All right, we're gonna stop here. 5 minutes.
Dr. Russell?
Yes.
What would be the test setup?
What you mean?
Like, will it be on lockdown browser?
Not this one. Not this one. I'm gonna make it open notes.
Okay, and we have until Wednesday at midnight to turn it in, or
no,
what's
I'm gonna
that?
open it on Wednesday. It's gonna be just like the other exams. I always give you like 2 days to finish it. So I'm gonna open it on Wednesday and then it's gonna close on Friday at midnight. Well, Friday
Okay.
at 11:59.
Yes, sir. Thank you.
Because midnight Friday is technically Saturday, right? So
Mm-hmm.
yeah, I had a long, big argument with a student about that several years ago. It can't be midnight Friday because that's Saturday. So 11:59. You'll be surprised what people try to
I would
nitpick.
think they would support the midnight so they can do, a
No,
few more
you'll be
minutes.
surprised. You'll be surprised what people like to